So we saw in this module that to deal with unstable gradients, there are three main things that we can do. One of them is batch normalization. Another one is changing initializers and making sure that we are choosing the correct activation functions with them, specifically non-saturating activation functions. And lastly, for RNNs, we can do gradient clipping. So let's go over them one by one and see how we can implement them on Python and Keras. So here I'm just creating a project kind of similar to the one that we did in the exercise, reading the data, normalizing the data, and then creating a model. Changing initializers and activation functions are actually quite simple. All you need to do is specify the activation function to be relu, celu, softmax, whatever you want. You can find a comprehensive list here. Also, you can just Google Keras initializers, Keras activation functions, and you'll find the documentations. But also here, there is like a nice and comprehensive list of everything together, of all the options that you have. If you want to change initializers, here you need to specify them inside your layer as kernel initializer to be hey, normal, or lacun uniform. And there are a lot of other options. If you do not specify anything, it will automatically be a glorot uniform weight initializing. So just so you know, if you want to use glorot, you don't have to specify anything. It will automatically be that one. But if you want to use relu, for example, as we said, hey, initializing is the best thing to use with relu activation functions. So you can specify it like this here. Or if you want to use celu as your activation function, lacun uniform kernel initializing would be the best for you. So this is how we specify them. And then we have batch normalization, which is also extremely simple to implement on Keras. So let's say we are creating our architecture here. What we do is we have a flattened, because let's say, again, we're working with the images. We are flattening the input to be 784 length list. And then we create a hidden layer and then another hidden layer and then a output layer. So to have batch normalization, basically all you have to do is to create a batch normalization layer in between your layers. So if I put this one here, that means that in between the first hidden layer and the second hidden layer, there will be a batch normalization. And the outputs from this first hidden layer will be normalized before being sent to the second hidden layer. And that's all you need to do. One thing that I want to point out here is that if you want to, as we talked about, you don't have to do the normalization separately from your model creation. You can just have batch normalization after the flattening layer or any other pre-processing layer that you have before your data is passed to your model at all, to any of the layers that you have. If you use batch normalization, your input will be normalized, so you don't have to do it separately like we did in the exercise previously. Another thing is that if you remember, when we were doing batch normalization, we have 4 parameters. So 2 of them were the trainable parameters. So we had the offset and the scale, right? These were basically learned. And we also had we were calculating the average and the variance or standard deviation of the inputs that we have. And those were the ones that will not be trained. They are basically learned from the data. So if you look at the summary after we create this model, you can see that there are some non-trainable parameters. And just to do a quick check, we see that we have 2 batch normalization layers. First one has 400 parameters. The second one has 1200 parameters, and in total they make 1600, right? And half of it, so basically there are 4 parameters, 2 trainable, 2 not trainable. So in total, half of the parameters that comes from batch normalization will be non-trainable. So half of 1600 is basically 800. So that means that we are thinking of it correctly and everything's fine. So just wanted to grab your attention to this point. One other point with batch normalization is that the people who came out with batch normalization actually claim that your model will be more accurate if you do batch normalization before you put your inputs into the activation function. So let's quickly remember how this works. So as you know, we have our inputs, right, from the previous layer or from the input layer. The inputs, let's call them X. How we calculate the output of a layer is by multiplying this input with the weights and adding biases. And to create the output of one layer, we also need to put all of this inside an activation function, right? So this is the output of one layer, and then we pass it to the next layer. But when you also include batch normalization in between here, the first one dense layer to the other dense layer, what you're doing is you also put a batch norm here after the activation function. You calculate some stuff, and then you pass things to the next layer. Well, what they claim is that in that paper where they came out with batch normalization is that it's better if you put the output of one layer into batch normalization before you put them inside the activation function. So basically this would go into the batch normalization, and then you apply the activation function on top of them. This is actually fairly simple to implement. So as you remember, normally what we do is inside the layer itself, we specify the activation function. Here, then we would not do that if we wanted to. So maybe this will be easier if I separate them from each other a little bit. Yes, so this is one hidden layer, and this is another hidden layer, and this is the output layer, right? So basically, we create our layer without any activation function in it, and we have the activation separately as a separate layer to be applied to our data, more specifically the output of this layer here after the batch normalization. And that way you are able to apply batch normalization to the outputs of any layer before the activation. One addition that they had there was that then you don't really have to have a bias for this layer. So as you remember, as I said, what we do is we multiply the input with the weight, add the bias, and then put it through activation. But here what we do is, because we have batch normalization, and if you remember in the batch normalization we have scaling and offsetting, we don't really need bias, because offsetting is also just adding some sort of value that is going to be trained, that is going to be learned, to our outputs. So if you also have bias, it's going to look like this, basically, or let's say offset, right? These values together do not need to be learned separately. So you can just have one of them and learn one of them. So what you can do is to say, I'm not going to use bias. There is not going to be any bias in this layer. The bias comes from the offset of the batch normalization. So that's kind of standard practice, what we need to do if we want to have batch normalization before activation function. The last thing that we learned that deals with unstable gradients is gradient clipping. That's also quite simple to implement. There are two ways how you can do that, very similar to each other. Basically, what you need to do is, while you're compiling your model, this is right before you fit the model. So that's you create the architecture of the model, and then you compile it, and then you fit it to the data, if you remember. What you need to do is you need to specify if you want to do gradient clipping inside the optimizer. So you can either create the optimizer as a separate variable and then pass it to the compile function, or do this also inside the compile function. That would be fine. So that's no problem. But what you need to specify is either the clip norm or the clip value parameters for the optimizers. I think this is possible for all the optimizers that you have. Again, as I said, you can go and check out the documentation for the specific optimizer that you're trying to use. But for all optimizers, you can do gradient clipping by specifying values for clip norm or clip value. And clip value is basically the normal gradient clipping that we learned. The values are clipped to a certain maximum and minimum point. So if you say 0.5, they are clipped to be minus 0.5 and plus 0.5 without any scaling. If you do clip norm, that is gradient clipping with normalization, then your values are basically squished together, so they're tightened or clipped while keeping the scale in between them to be between -1 and 1. So we're clipping with normalization and clipping with just using the value. Those are the two options that we have to implement gradient clipping. So hope everything was clear. Once again, if you have any questions, do not hesitate to ask them in the comment section below. So